Welcome everybody. My name is Rafał Łochowski. I am from Warsaw School of Economics, and I would like to present my and Witold Bedno's results on moments and tails of heating times of Bessel processes and convolutions of elementary mixtures of exponential distributions, which are very much related to the moments, to the heating times of Bessel processes. And I, of course, would like to thank organizers of GPS days at Mannheim for giving me possibility to talk at this conference. So let us start with definition of Bessel processes. Bessel processes, the dimensional Bessel process is related very much to Wiener, d-dimensional Wiener process, because it is radial part of this Wiener process, but it may be defined for not only for integer deltas, integer dimensions, but delta dimensional Bessel process may be defined as the square root of a process which is defined by the following stochastic integral equation. So here we have starting point x0 Bessel process starting from x0 greater or equal 0, and here we have the equation. Then here we have stochastic integral where driven by standard Brownian motion. And we will be interested in first in the heating times of Bessel processes, which are heating time of level C, which can be defined in this way. And we will assume throughout this presentation that C is greater than 0. So we start from lower level than C. And actually it appeared that there is not much known about the laws of these tails. There is, however, there is a quite rich history of investigation of these tails, but I will skip this due to lack of time. But what we were able to let us focus what we were able to obtain. First estimates which we obtained were upper estimates for right tails and upper estimates for left tails of the heating time. So here we have expectation which reads like this, and what is the method to obtain these estimates? Actually, it is not very difficult. We need to investigate some exponent of square of Bessel process stopped at time tau c, and apply some optimization. So these were the very first estimate, and we can see that they give quite a strong concentration of this tau around this its mean. But the estimates like this, they have also some application in large deviation theory. For example, estimate 3 can be translated into possibility of probability of fast exit of a standard multidimensional Brownian motion from a ball. And these kind of estimates are used in large deviation theory. For example, in book by Dembo and Cetouni, we have the following estimate for living standard d-dimensional Brownian motion starting from 0 from the ball with radius c. And here we have both dimension and c and probability that this happens until time capital T may be estimated in this way. Our estimate gives the following bound, and and this is applicable when c square over t is greater than d, which makes sense, since when we have opposite inequality, then both this quantity and our estimate give probabilities of order 1. This can give even bigger when d is quite large. But when this relation holds, we get this kind of estimate. Even when we have even better estimate, like for example, c square over t is greater than 2d, then our estimate is much better than this, since we don't have this term in front of exponent, and more important, we don't have this term in the exponent, which is and nothing else like of this order. And this becomes like less than more than 1/2 when c square over t is greater than 2. So we got quite a nice result for, and we were asking if these estimates are optimal. So I will talk a little bit later about left tails, but let us talk about now about representation of tau c and about right tails. So there is very nice representation of tau c in terms of so-called convolution of elementary mixtures of exponential distribution. This is due to Kent. And elementary mixtures of exponential distribution are distributions which have atom at 0, but conditioned on the event that they are positive, they have just exponential distribution. And for tau c, these mixtures have the following parameter for exponential distribution. Here we have consecutive zeros of Bessel functions of first kind. Using this estimate, this representation, we were able to and general estimates obtained for general convolutions of elementary mixtures of exponential distributions, which could be obtained using some results of Efim Gluskin and Stanisław Kwapień. This estimate looks like this. We were able to obtain estimates of central moments and ordinary moments of time tau c, but more importantly, we were able to obtain estimates of right tails using these estimates of moments and using Paley-Zygmunt inequality and Chebyshev's inequality, and these estimates look like this. So there are some universal constants, gamma 1, gamma 2, gamma 3, gamma 4, which do not depend on any of these parameters, c, delta, t, x0, and we have the following estimates for the right tails of tau times tau c. When we they can be there can be even some constructed some algorithm to construct to calculate these estimates more effectively. What about left tails? So left tails were already, while upper estimate was already presented. What about lower? Using also some martingale, exponential martingale, we were able to obtain lower estimate, which look like this. And the coefficients are similar, but this estimate works only for large deltas, which is useful in large deviation theory. But when we want to have estimates for small deltas, we need to use some interlacing property of Bessel function, of zeros of Bessel function, which looks like this. And then we obtain the following estimates. Here we have tails of the first elementary mixture of exponential distribution, which cannot be omitted, since it can be much smaller than this part. So these estimates hold now for any delta. Okay, that's all which I wanted to present. Let me also show 2 slides with some references. And this is what I wanted to present, and I would like to thank you for your attention.